Alice send 00 to Bob, and then there must be one of 00, 10, or 10 or 11 received by Bob. And if Bob received 11, then Bob doesn't know that there is an error occurred during transmitting the word. Yeah. So in order to understand if there is an error occurs, then we have to add redundancy, something like this. Yeah. So C, yeah, become 000, 100, 011, and so on. And information rate is 2/3. And C transmit 3 bits for a message of 2 bits. Yeah. The scheme allows for one error detection, but no error correction. Why? Yeah. Suppose we transfer 000, yeah, Alice transfer 000, and Bob received 010, yeah. So the transfer word is 000, and the received word is 010. So Bob knows that there is an error because 010 is not one of these code words. So Bob can detect that there is an error during the transmission. But in this case, Bob cannot correct the error that occurs. Yeah. Another example is binary repetition code. Yeah. A is the same as before, this 0 and 1, and N is K times 2R plus 1, where K and R are in natural number. And message are element in A to the K, that is K tuples, yeah, for fixed K. And then encoding, how to encode, yeah, take any message and repeat it to R plus 1 time for a chosen R. So for example, K is 2 and R is 2, then 0, 1 is repeat, the digit 0 is repeat by 2 times 2 plus 2R, 4 plus 1, 2, that is 10. Yeah. So this repeat by 5 and 1 repeat by 5. And then how to decode? Yeah, we check the first digit. Yeah, the first digit is we considering the first digit, and this occur in the odd position. So we can detect that 0 is the position of 0 in the odd, that is 1, 3, 5, 7, and 9. And position of 1 is in the second, 4th, 6, 8, and 10. Yeah. So the decoding method is considering the odd position and choose the value that appear more frequently at the received word. Similarly for the even position. In general, for K and R are in natural number, the rate is low. Yeah? The rate is 1/2R plus 1. But the code can correct up to R error. Yeah? And so we can always construct a coding system that can correct R error for every R in this case. And this definition of Hamming distance. Yeah. For X and Y in AN, we define the distance or Hamming distance denoted by dxy is the number position at which their entries differ. Yeah. So Txi is the number of I in 1 to the n, where xi is not the same as yi. So this is the example. Yeah. X is over A, that is A is Z5. Then for X is 0, 1, 2, 3, 4, and Y is 1, 4, 3, 3, 4. Then Dxy, the distance between X and Y is the first position, second position, third position. Yeah. The fourth and fifth position are the same, so the distance of xy is 3. So the Hamming distance is a metric. Yeah. Minimum distance, yeah, for a code C of at least 2, the number of code is 2, its minimum distance of C is defined by minimum of dxy, where x and y are in C and x is not the same as y. And the parameter of the code, yeah, is the length, that is in this case the length n, and the size is the number of code word in that code, and the distance. Distance mean in this case it's minimum distance of the code. And the notation is NMD, yeah, over alphabet A of Q element. So NMD are called parameter of C. Yeah. Most of the main problem of the coding theory is doing with the parameters of C. So for example, we have C like this. So the parameter, the length of 5, and the number of code word is 3, and the distance we can compute this as the distance is 2. Yeah. And then the definition of error detecting. Suppose we are given U is a natural number. A code C is called an U error detecting if error is at least 1 and at most U position. Send a code word into a non-code word. Yeah. So this is this code is capable to detect up to U error introduced by the channel. And C is exactly U error detecting if it is U error detecting but not U plus 1 error detecting. And the theorem says that if C is U error detecting, then the distance of C is greater or equal to U plus 1. And if the distance of C is greater or equal to U plus 1, then C is U error detecting. In other words, that a code of minimum distance D is exactly D minus 1 error detecting. And then definition of correction. Again, we are given phi is a natural number. A code C is phi error correcting if it can correct error up to phi position. Yeah. So if the channel introduces up to phi error, then the system can correct the error. And C is exactly phi error correcting if it is phi error correcting but not phi plus 1 error correcting. And the theorem says that if C is error correcting, then the distance of C is greater or equal to 2 times phi plus 1. And if the distance of C is greater or equal to 2 phi plus 1, then C is phi error correcting. A code of minimum distance D is exactly the floor of D minus 1 over 2 error correcting.